Okay, welcome to lesson 19 of module 4. The title of this lesson is The Graph of a Linear Equation in Two Variables is a Line. So in this lesson, we're going to pull together a lot of the little parts that we showed in lessons 15 through 18, and we'll show a formal proof that the graph of a linear equation in the form of y equals mx plus b is actually a line. And so to do that, we're gonna go through some formal proofs. We will be skipping some of the exercises in this lesson in favor of looking at the formal proof. The other thing that we'll look at in this lesson is a third way to graph linear equations on the coordinate plane using the x and y intercept. So we've seen how we can make a table of values. We can make an XY table. And if we have an equation in the form y equals mx plus b, we can use the slope and the y-intercept to graph an equation. So in the rest of this lesson, we're going to see that because by joining any 2 points, that defines the line, we're going to use something called graphing with intercepts. So that will be toward the end of the lesson. Okay, let's get going. Okay, so we want to show that given 2 points, P and Q, which are solutions to y equals mx plus b, and also given the line L that passes through those 2 points, we want to show that any solution to y equals mx plus b, not just P and Q, but any point that is a solution to y equals mx plus b is on line L. And then also, we have to show that any point that's on line L is a solution to y equals mx plus b. And if we can show those 2 things, then we will know beyond a shadow of a doubt that the graph of y equals mx plus b is the line passing through any 2 solutions to y equals mx plus b. So that lets us know that we only have to find 2 points on the line in order to graph it, and that the graph will be aligned for any value of x and y. Okay, so let's move ahead with that proof. Okay, so to prove those 2 things, and we'll revisit it. We can revisit as we go through this. We're going to use a specific example. We're going to use y equals 2x plus 3, and I've chosen 2 points, P and Q. P is 0, 3, which is obviously the y-intercept, and Q is 4, 11. So you can verify that both of those are solutions to the equation y equals 2x plus 3. Okay, I forgot to say that you don't have this in your notes. So if you want to quickly get a piece of graph paper and sketch the equation y equals 2x plus 3, you can follow along and take some notes. Because what we're going to do is we're going to use this method that we're going to develop right now and do exercise 1, which is the general proof for any y equals mx plus b using the same technique. So go ahead and grab a piece of graph paper and sketch this out. Okay, so what we have here is line L, and it goes through the points P and Q, like we stated in the beginning. So here's line L going through points P and Q. So what we're trying to show is that any point that's a solution to y equals 2x plus 3, to that equation, is on line L. Okay, so we're going to start with a diagram that shows point R, and we're saying point R is a solution to y equals 2x plus 3, but we've drawn it so that it's not on line L. So what we need to do is to show, if we have it here on line L prime, right here. Okay, so if we can show that line L prime has a slope of 2, then we'll know that line L prime is the same as line L, and that point R, which is just an arbitrary point that's a solution to this equation, would have to be on line L too. Okay, so that's our goal. Our goal is to show that the slope of L prime is 2. Because, as we talked about in the last lesson, there are not two lines that pass through a given point with the same slope. There's only one. And so if we can show that this line has a slope of 2, then they're the same line. Okay, so how are we going to do that? Okay, so we're going to talk about point R, which has coordinates R1, R2, and point P, which has coordinates P1, P2. And we know that since R2 is a solution to this equation here, we know that R2, which is the y-coordinate, has to equal 2 times R1 plus 3. And we know that P2 has to equal 2 times P1 plus 3, because R1 and P1 are just the x-coordinates. So now we can write an expression for the slope of L prime. And remember, we want to show that it's 2. So the slope of L prime is the difference in the y-coordinates. So we've got 2P1 plus 3 minus 2R1 plus 3. I'll put parentheses around that. Divided by the difference in the x-coordinates. Remember, it's this ratio right here. So the difference in the x-coordinates is going to be P1 minus R1. Okay, so we want to, and this should look familiar because we did this in, I think it was lesson 17. So when we expand this out, the expression in the numerator becomes 2 times P1 plus 3 minus 2 times R1 minus 3. Remember, we have to distribute that negative sign into both terms of that expression in parentheses. Okay, so let's look at this. So what does that simplify to? Well, first let's write the denominator again, P1 minus R1. So this just becomes 2P1. So notice I've got a plus 3 and a minus 3, which cancels out to 0. So I've got 2P1 minus 2R1 over P1 minus R1. And I'm running out of room, so I'm going to show you the next couple steps just by erasing here. So you can see that this is going to simplify to 2, and here's how. So if I factor, and I'm going to factor this out by erasing, I can factor that 2 out, and let's just use a different color here, by putting it out front. So this expression and this expression are the same. This is just 2 times the quantity P1 minus R1. And then if you notice, P1 minus R1 is the same value as P1 minus R1 in the denominator. So that is a factor of 1. So the slope of L1 we showed to be 2. Therefore, what we know is that any point R, any point that is a solution to this equation, y equals 2x plus 3, has to lie on that line L that we first defined by just drawing it through any two random solutions there. So we've shown part 1 of that proof. Okay, and just to kind of restate, we did it by using the fact that there's only one line passing through a given point with a given slope. So if this is going to go through point P and have a slope of 2, then this line L prime that we drew has to be the same as line L. Okay, so there's our proof. So we're only done with part of it though. Now we have to prove part 2. Okay, so for part 2, it's kind of the opposite. We have that line L that goes through points P and Q. And what we're going to do is pick any random point on line L. We're going to call it S. And we want to check to see if it's a solution to y equals 2x plus 3. Okay, so the coordinates of S, the coordinates of point S, we'll call S1 for the x coordinate and S2. So we've got this point S. Okay, and we're also going to use the point P, which is, we know, is on the line, and the coordinates of point P are 0, 3. So we've got S and P, and we can write an expression for the slope. So the slope of line L in terms of S and P is going to be the difference in the y, which will be S2 minus 3. Here's my y coordinates, S2, and my y coordinate 3. And then that's going to be over the difference in S, which is going to be S1 minus 0. Okay, so the slope of L is equal to this expression right here. But what do we know about the slope of L? Well, we know that the slope of line L is 2. And so we can substitute 2 for the slope of L, and we get 2 is equal to S2 minus 3 over S1. And I just wrote S1 minus 0 as S1. Okay, and then if we cross multiply, let's do this in a different color here. I'm going to write this as 2 over 1, and then I can multiply across and get a new equation. Or I could think of this as just multiplying both sides by S1. They're equivalent, right? If I multiply both sides by S1, then this cancels, and I get 2S1 is equal to S2 minus 3. And if I rearrange that, I'm going to add 3 to both sides here. And I have a reason for doing that. Add 3 to both sides, and I'm going to get this expression. I'll get 2S1 plus 3 is equal to S2. And look at that for a second. I'm going to circle it. That expression there tells us that S1, S2, our point S, is a solution to 2x plus 3. Because what was S2? S2 was just y. S1 was x. So this could be thought of as y is equal to 2x plus 3. So what we showed was that picking any random point on the line L, knowing that it had a slope of 2, gave us the fact that that point is a solution to the equation y equals mx plus b. So we've shown part 1 and part 2 that that if we pick a solution to y equals 2x plus 3, that it's on that line that we drew growing through 2 solutions to the equation, and that if we pick a point on that line that goes through those 2 points, then it will be a solution to the equation. So the proof is complete, but we've only done it for y equals 2x plus 3. So exercise 1 is going to walk us through a proof, a general proof, using the exact same technique. So you do have this in your notes, so we can read it together. And our theorem that we're trying to prove is that the graph of a linear equation y equals mx plus b is a non-vertical line with slope m and passing through 0b, where b is a constant. Okay, so we're going to prove the theorem by walking through their steps, which are going to be exactly the same as the steps we just went through a minute ago for the specific proof. Okay, so we're given 2 points, P and Q, that are solutions of y equals mx plus b, and then there's a line L that passes through those points P and Q. Okay, so we want to show that any point that's on the graph of y equals mx plus b has to be on that line L, and that any point on that line L is also a solution of y equals mx plus b. Okay, so we have to prove those two things separately. So part A is going to walk us through the proof of 1. Okay, so this is going to kind of again be sort of that proof by contradiction. We're going to contradict this diagram here. So what is this diagram showing? Well, you can see points P and Q in line L right here. So points P, Q, and then the line L that goes through them. And remember, P and Q are solutions to y equals mx plus b. Okay. So the slope between points P and Q has to be m. We do know that. Okay, so we're going to let R be any point on the graph of y equals mx plus b. And we want to show that point R is on line L. Okay, so they've drawn this kind of crazy curve for the graph of y equals mx plus b. So we're kind of assuming that it's not a line. So we're saying it's some, it's some curve that goes like this. It goes through points P and Q, but it's not a line. All right, so we know that it is, but so we're going to contradict that idea. Okay, so we're assuming that it's not a line, or that R is not on L, and we're going to show that it has to be. So, like it says here, assume the graph looks like the diagram below, where R is on a different line. It's on line L prime right here. So we're asked to see what is the slope of line L. So let's do that now. Okay, so the slope of line L, like we said, has to be m, because P and Q are solutions to y equals mx plus b. And we've already shown that the slope between any two solutions to y equals mx plus b is m. Okay, so we know that that slope has to be m. Okay, so now we're asked, what is the slope of line L prime? This line that contains the point R. So we know that R is a solution to y equals mx plus b. So if the coordinates of R are R1 and R2, then I know that R2 is equal to m times R1 plus B. So, so point R's coordinates could be thought of as R1 and M times R1 plus B. Those are the coordinates of point R. And we have this other point P, and so its coordinates would be P1 and then M times P1 plus B. So we have these points P and R, so we can write an expression for the slope of L prime. Okay, so why don't you work on that? What is the slope of L prime? How could you express that using the coordinates of P and R? The slope of L prime. And remember, our goal is going to be to show that the slope of L prime is equal to M. So we're going to go through that. So go ahead and take a minute and see if you can write an expression for the slope of L prime. Okay, well, hopefully you paused quickly. So slope of L prime is going to be the difference in the y coordinates. So that would be these right over here. The y coordinates are m times p1 plus b and m times r1 plus b. This should look very familiar. It's the exact same thing we've done in lesson 17 and we just did. And then the difference in the x coordinates is right here, p1 minus r1. All right, so go ahead and pause. See if you can go through the reorganization of this to show that the slope of line L prime has to be this number m. Okay, so I'm gonna pause and I'll write it, and you pause and write it, and then we'll double check here. Okay, so by expanding those terms and noticing that the positive b and negative b become 0 when added together, and factoring that m out, and then canceling that common factor, then we found that the slope of L prime is m. So what can we conclude about L and L prime? Well, L and L prime both go through, let's go back and look at it. They both go through this point P. They both go through point P, and they have the same slope, so they are the same line. So this point R that we previously drew down here has to be up on this line L. So here we could conclude about lines L and L prime, something like they are the same line. And we know that because you can't have, there's only one line passing through a given point with a given slope. And so we showed that their slopes are the same, therefore they're the same line. Okay, so we've done part one, that if we choose a point that is a solution to y equals mx plus b, then it has to be on that line. And now we're going to choose a random point S on line L, and we're going to show that S is a solution to y equals mx plus b. So any point that's on this line is a solution to y equals mx plus b. And so we're given a hint here to use the point 0b as one of the points. Okay, so I don't have enough room to do it right here, so I'm just going to move to a new screen. We want to show that S is a solution to y equals mx plus b. So S has coordinates S1 and S2, the x and y coordinates of S. So I'm going to use point S and also the point 0b, which is also a solution to y equals mx plus b. If I use those 2 points, I can write an expression for the slope. So the slope of line L is the difference in the y, so it's S2 minus b, and over the difference in the x. And I just realized I'm spoiling your fun. So what I want you to do now is to work through the rest of this part and see if you can show that S is a solution to y equals mx plus b. So go ahead and pause it now. I've done some of this for you. I've got you started. Continue on your own, and then if you get stuck or if you want to check your results, then you can come back. Okay, so we've written an expression for the slope of line L, but we know that that slope we know that the slope of L is m. Because, why? Because it goes through points P and Q, which are solutions to y equals mx plus b. So we know it equals m. So I'm just going to substitute m for that slope, and maybe you did that too. And so m is equal to S2 minus b over S1. Okay, and then we can multiply both sides of this equation by S1, or we can cross multiply, whichever you prefer. And I'm going to rewrite this equation now. So we've got m times S1 is equal to, this is canceling out, S2 minus b. So now what I want to do is add b to both sides here. And I get that m times S1 plus b is equal to S2. And this expression tells me that point S with coordinates S1, S2 is a solution to y equals mx plus b. Okay, so this is pretty cool. So we have shown that the graph of a linear equation is a line. Okay, so because we went through all that proof, you can go ahead and skip exercises 2 through 8. We don't need to do those. Exercises 2 through 8 just give lots of examples, specific examples, and informally proves the same thing that we just went through a formal proof of. So we're going to go ahead and skip those. You're welcome to look at them if you'd like, of course. We're going to move on to an example that you don't have in your notes. And then it's just like exercises 9 through 11. So watch me do example 1, and then you can do exercises 9 through 11 on your own. Okay, so like I said in the opening screen, the other goal of this lesson was to give you another tool for graphing equations. So we've done XY tables, and we've done using the y-intercept and the slope. And now we're going to do something called finding the x and y intercepts, so graphing by using intercepts. Okay, so when you have an equation that's in this form, something like this, 2x plus 3y equals 9, that's standard form. It's not in slope-intercept form, so it's not immediately apparent what the slope is and what the y-intercept is. So I'm going to use a different method, okay? So what I want to find is, I want to find where the graph crosses the x-axis and where the graph crosses the y-axis. Because if I can do that, I'll have 2 points, and then I can graph the line. Okay, so by setting x equal to 0, we can find the y-intercept. So we can say 2 times 0 plus 3 times y is equal to 9, and so that becomes 3y equals 9 and y equals 3. So the y-intercept is at the point 0, 3, right there. So it'd be the point x equals 0, y equals 3 is a solution to that equation. And then to find the x-intercept, we're going to set y equal to 0. So that would be 2 times x plus 3 times 0 equals 9. So 2x equals 9, and x would equal 9 halves, or 4.5, 4.5. All right, so we can graph that point. Right there at 4.5, and draw the line through those 2 points. Something like that. And we can label the other intercepts. So this point would be 4.50. Okay, so graphing by intercepts is really easy. It's really just finding two really simple points to solve for. First by setting x equal to 0 to get the y-intercept, and then setting y equal to 0 to get the x-intercept. Okay, so after that, you have exercise 9, 10, and 11 to graph using intercepts. So these are in standard form or close to it. And so you can solve for the intercepts and then grab a piece of graph paper and graph those. Okay, so I'm gonna pause if you want to pause the video and do that, and then I will show you the solutions. Okay, so for this first one, if we set x equal to 0, we would have negative 3 times 0 plus 8y is equal to 24. So that simplifies to 8y is 24. Dividing by 8, we see that y is equal to 3. So the point x equals 0, y equals 3 is a solution to that equation. Now to find the x-intercept, we want the point where y is 0. So we're going to insert it here. So we'd have negative 3x plus 8 times 0 is equal to 24. And so negative 3x equals 24. Dividing by negative 3, we'd get that x equals negative 8. So the x-intercept is negative 8, 0. So now if I want to plot those 2 points on this graph, the y-intercept is at 0, 3, right there. The x-intercept is at negative 8. Oops. Right there. And we can draw the line between those 2 points right about there. Okay, so that's exercise 9. Let's look at exercise 10. We want the y-intercept, which is going to be the point where x is 0. And we want the x-intercept, which is the x-coordinate where y is 0. So we're just going to insert 0 into the equation and figure it out. So 0 minus 6y is equal to 15. And so negative 6y is equal to 15. So y is equal to negative 15 sixths. And that would be the y-intercept there. And so for the x-intercept, we're going to set y equal to 0. So we'll get x minus 6 times 0 is equal to 15. So this simplifies, since 6 times 0 is 0, x equals 15. So the point 15, 0 is on the graph, and the point 0, negative 15 sixths is on the graph. Negative 15 sixths. Okay, so let's graph the X-intercept. It is at 15, 0. So there's 5, 2, 3, 4, 10, right there. And let's simplify negative 15 sixths so that we can see what that, where to plot that. It's 2 and something. So if we simplify that by dividing top and bottom by 3, we're going to get negative 5 halves, which is negative 2 1/2. So we can plot that on the y-axis right there. Okay, and we'll connect those with a line going through the 2 points. Okay, and so the line would be right there. Okay, so that's exercise 10. Let's look at exercise 11. Exercise 11, once again, we want to find the X-intercept where y is 0 and the y-intercept where x is 0. Okay, so first we'll put in 0 for x, so 4 times 0 plus 3y is 21, and so this is 3y equals 21, and y equals 7. So when x is 0, y is 7, and when y is 0, this becomes, notice the 3 times 0 is going to drop out, so this becomes 4x equals 21, and x is equal to 21 fourths. Okay, so 21 fourths, when I go to plot that, I'm going to think of that as 5 and 1/4. This 5 fourths, or yeah, 5 wholes would be 20 fourths and 1 more. Okay, so 21 fourths. All right, so we're going to graph those two. They're both positive. So, okay, so here's a pair of axes that we can graph on. So the y-intercept is 7. It's at the point 0, 7 right here. The x-intercept is at 5 1/4. So 21 1/4, about right there. And we can draw a line connecting those 2 points. Okay, so there's exercise 11. So in this lesson, we have looked at a proof that the graph of a linear equation is a line. So we know that a linear equation can be graphed using just 2 points, and we can do that using the x-intercept and y-intercept when it's convenient. So this summarizes that method of using the intercepts to graph. So now we have 3 methods that we'll use depending on what form our equation's in. So we can just create an xy table and find a couple points. We can find the x and y intercepts, or if the equation's in slope-intercept form, we can use the y-intercept and then use the slope to find another point. Okay, so there's lots of different ways to go about that. Okay, so that's lesson 19. I'll see you back here for lesson 20.